All right, this is the video that I'm doing for November 5th and November 8th, assuming this is just in case I'm not here on those days, in case I'm having my baby. So here is the video of what you guys will be doing if I'm gone. So the first thing, let's see. Cut, color out atomic tiles, 25 minutes. Okay, Ziploc bags for the tiles. If I don't make it and I don't have you any Ziplocs, you can go to the front office and they have these really, really ugly envelopes from Highland High School. Just get the front office to give you a bunch of these. And then we're also going to do notes 22 and homework 4.4, some of it. So that's going to be the schedule for this video in case I'm gone Friday or Monday, the 5th or the 8th. So the first thing is says to cut and color the atomic tiles. And if you go to your packet, your new packet, term 2 packet, and go all the way to, let's see, they're in here somewhere. All right, so if you go to your packet and then go almost all the way to the back, not quite the very back. So very back page is the practice test, and then one more here. This is what you're looking for. You're looking for a page that has a bunch of little octagons on it and lots of different elements. And the first thing that I'm going to have you do is color it. It doesn't super duper matter how you color it, but there is somewhat of a color scheme that the chemistry people use for when they put elements together. Like they make these little Legos, and they have a color-coded system. Carbon's always black, and blah, blah, blah. Like they have all of these. So I'm not really concerned with the coloring myself, but this is the colors that I have used in the past. Doesn't really matter as long as you have a system that works for you. Couple of things. You're going to want to leave the white dots unshaded, keep them white. And note, you must cut these out into octagons. If you only cut them into squares, they will not work correctly. So we're going to be trying to build things with our little sheets of paper, and they won't work if you leave them in square form. They need to be cut full octagons. So this is where you'll pause the video and take about 25 minutes to cut them into what I already have done here. I didn't color these ones, but you're going to cut them into little octagons like this. So 25 minutes on the timer. I'm not actually going to sit here and time you for 25 minutes, but go ahead and take 25 to 30 minutes to cut these out and unpause the video once that time has passed. Once you've got them all cut out, we are going to use these today, but just so we don't lose them, put them in your envelope, and somewhere on your envelope, I'd like you to write your name. You guys don't know my name, it's a secret. Write your name on your envelope so that if you leave it in the classroom on accident, ooh, that's blurry. If you leave it in the classroom on accident, that we'll be able to get it back to you. And then, as the paper said, we're going to do notes 22. So pull out your notebook for that. Let's see, notes 22 is on covalent bonding / Lewis structures. I don't really like that pen, it's too light. covalent bonding. Oh, it's 22. Now in ionic bonding was where the electrons were being completely transferred so that there were charges happening. But in covalent bonding, we've got the word co, meaning like together. If you are cooperating or cooperating, you are working together. If you are co-workers, you work together. So covalent, the word valent is coming from, we've already learned this word. We haven't used it a super ton, but valence electrons are the electrons in the outermost ring. So they're sharing together they're sharing the outermost ring of electrons. I don't know what that is. I was just drawing. Okay. That's a bullet, I guess. I don't like it. It's just going to be a scribble. Sharing electrons to form a covalent bond. This occurs when you have two nonmetals, two or more nonmetals. So up here, right, here's my periodic table. The metals are these brown ones. Metals are brown. Non-metals, this is difficult. It was hard. Non-metals are here. They're the red ones. So we've got multiple kind of red ones bonding together. That's covalent. Sharing electrons to form a covalent bond occurs between two or more nonmetals. Okay, so basically, let's see, you've heard of like single bonds and double bonds and things like that, and you've probably seen drawings where they come together. We're going to make a little chart of the three types of bonds, like single bond, double bond, triple bond. So here's going to be our little table. The first column will be the number of electrons that are present. Then number of pairs of electrons. Bond type. Bond length. And the last will be bond strength. Ooh, I was going to highlight that, but that is going to make that very, very smudgy. So pass. Ooh, maybe if I use it different, like an actual highlighter. That is a little bit better, but I'm still kind of regretting my decision. Okay, we're comparing a single bond to a double bond to a triple bond. Extend my chart so that there's adequate room for all. A single bond is where you've got one pair of electrons that are coming together. One pair of electrons is going to be 2 electrons, right? So two dots coming together, and they're going to bond. A double bond would be 2 pairs of electrons coming together. So like 1, 2, there's a pair, 3, 4, there's a pair. We've got 4 electrons coming together. It would look like this, double the amount of bonding. So 3 pairs of electrons would be 6 of them together. There we go. Now over here, I just kind of drew them all the same, like 1, 2, 3, but like no other differences. It turns out that there are differences in terms of length and strength. A single bond, this is like only having one piece of string, like holding you together, like one rubber band, versus 3 is much stronger. So the strongest of the bonds is going to be the triple. Duh, because it has 3 pairs of electrons in the center, keeping it together. The weakest will be that single bond, and the double bond will be somewhere in the middle with medium strength. This also has an effect on the length. A single bond, since it's weak, it can't hold the 2 pieces very close together. Whereas a triple bond, it's like got way more strength going on. So the distance is a lot shorter. So bond length, this one is the longest. This one would be the shortest. And somewhere in the middle, I'll do it in a different color. Maybe like here and here and here. The double bond is like the mediumest length. So got really long, and we've got medium, and then our shortest little guy down here. More on that later. What we're trying to figure out though, more than like the length and the strength and all that, what we're trying to figure out is how do we draw molecules and put them together. This is just important because this is kind of what they're going to look like when we draw them. So down here, this next part will be called Lewis structures. After Gilbert Lewis, is the guy that kind of came up with these. And what the point of this is to show how covalent molecules are bonded, aka how are the atoms connected. They don't necessarily show you the correct shape, but they will show you how it's connected. So that's why I want you to highlight more like how they are connected together. It's a really important piece. So let's do, for example, let's try and draw a water molecule. You know that it's H2O, 2 hydrogens, 1 oxygen. And we know that it's a covalent molecule because if I look on my periodic table, oxygen, here, is that it? Here? No, here. This is difficult. How do you guys do this on TikTok? Okay, so oxygen is non-metal, and hydrogen over here is red, non-metal. 2 nonmetals sharing electrons. Why is my hair weird? I was so self-conscious. Anyway, we've got 2 nonmetals sharing electrons, and we're going to try and put them together. So with your tiles from the envelope, you're going to need to pull out your oxygens and your hydrogens. And the reason it matters is because, like, take a look, they're not all the same. Even if you pull out 2 carbons, there's different types of carbons and how they bond. So you'll need some hydrogens, and luckily all of those are the same. But fish through your oxygens because you have a few different types of oxygens that we'll need to choose which is the correct one for this problem. Your 2 choices for oxygens look like this. There's one that has 2 black dots on top, and then ones that are on the side. These are the electrons that are in the outsidemost ring of oxygen. Oxygen has 1, 2, 3, 4, 5, 6 electrons on the outside of its shell. This would come from a Bohr model if you wanted to draw it out from the last unit. Remember, we had like the nucleus in the middle, and then we had rings on the outside. And oxygen from the periodic table, you don't have to write this down. Oxygen has 8 electrons, so 1, 2 in the first ring, 3, 4, 5, 6, 7, 8. There were 2 in the first ring, then 6 in the second ring, and this 1, 2, 3, 4, 5, 6 is showing that we've got 6 here. That's what the valence is showing. But you don't need to know that to do these problems, but that's where it's coming from. Hopefully you found your oxygens here. And these are just the 2 orientations. What if the shared electrons are separated? What if the shared electrons are together? For these problems, the dots that are shaded darker, shaded equals shared. Shaded electrons are shared electrons. We need to get all of the black dots to have a pair. if I do this, this does not work. Do you see how I'm trying to get like a single to bond with a double? That doesn't work. I could get, if I wanted, I could take the oxygen and bond it to a carbon. You can see how it's like 2 and 2. I could connect them. Boop. But I can't with this single. So even though we have two choices of oxygen for our water molecule, we know we're going to go with this one because the hydrogens can only single bond. So get rid of this one. Boop. Goodbye. And we've got oxygen. And this is how I'm lining it up. We're trying to get all of the shaded ones that are shared. We need them to connect. So once you've got this, trace your little shape onto your notebook. I would say just to glue these in, but then if you glue them in, you won't be able to use them for other problems. So here's the oxygen. 1 dot there, 1 dot there, and some empty ones up here. See, same, look, drew it perfectly. So there's my oxygen. I need to also trace my hydrogen. Hydrogen has 1 dot. There's the hydrogen. Very tedious activity. And there's my other ones. So I basically have this that I've redrawn. Pause the video if you need an extra minute, but I'm going to move on here. The shaded dots are shared. So draw some connection lines, just like up here in this part of the notes where we had 2 dots that were shared and we drew a line. 2 dots shared. Whoop, it's a single bond. 2 dots shared. Whoop, single bond. It would be very tedious to have to draw the octagons every single time. So from here on out, you're going to use these to make structures, but then to draw this shape, you could just do the following. You could just convert the picture to look like this. I still have an oxygen in the middle. Let's see, an oxygen, hydrogen, hydrogen, single bond here, here, and 2 dots and 2 dots. You can do them however you want. You can leave them like circles and clear. You can dot them in normally. Either way is fine, but the reason that they're clear on your tiles versus not is so that you know which ones you're connecting. So this picture that you made with the tiles would turn into this Lewis structure for water. It shows us how the water is connected. Water has 2 single bonds and 2 lone pairs. Lone pairs are what we call these electrons up here that are not shared. Shaded equals shared, and if they are not shaded, then they are not shared, obviously, but specifically we're going to call these lone pairs of electrons. Water is a molecule that has 2 single bonds and 2 lone pairs. Sometimes for visual aesthetic stuff, Sometimes people will put these little domes like this on the outside of the lone pair. Either way is fine. That's why I did it in pencil so that I could erase it if you didn't like it. Oh no, but it's smudgy. So I don't know what I usually do. I go back and forth. But there's my lone pairs. So try another one. Over here on this other side, here was our example for water. Do a new example. Let's do NH3, which is called ammonia. You don't know that. You'll sift through, find all the nitrogens that you have. There should be a nitrogen that looks like this, a nitrogen that looks, there's 3 different kinds. I haven't found them all yet. There's another one. And I am not finding my 3rd nitrogen. Maybe I dropped it somewhere. Oh, I found it. Okay. Also, if you lose one, then just take one, flip it over, and just draw a new one that you need on the back. That's my little pro tip if you lose any. So these are my nitrogens that I can choose from. I need 1 nitrogen and 3 hydrogens. I obviously do not want this triple bond nitrogen because, like, how is a triple bond nitrogen supposed to pair with a single bond hydrogen? That doesn't work. So nix on this one, but later in some of the problems we'll do, we can bond this to other stuff. Like there is one of your carbon atoms, this one here, is a triple bonded carbon. We could put these 2 together and make a triple bond, but only because they both have the same number of connected dots. This nitrogen could make a double bond, but it's not going to work out so well because we don't have anything that like matches with it. This carbon matches, but we need 3 hydrogens. So this is the one we're looking at, nitrogen and 3 hydrogens around it. I'm not going to bother drawing out the full octagon again. I'm just going to kind of move this over here as a reference on how to draw this. And try and copy it here. Nitrogen in the middle. Single bond connection to a hydrogen. 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 And don't forget that it has a lone pair on top. You can leave it like this, or if you prefer, like me, you can put a little dome on it so that you can keep track of your lone pair. Last example, hopefully it fits on your page. Try carbon dioxide, CO2. And for this one, you're going to need the double bonded carbon. The double bonded carbon, and this is just guess and check. You just have to get more experience by trying it out. It's like a Sudoku puzzle. You try it, see if it works, and if it doesn't, try something else. So double bonded carbon, I need my double bonded oxygens to make CO2. Carbon. Let me turn it this way because I have a little bit more space. Oxygen, oxygen. There's my molecule. So carbon in the middle. Double bonds to an oxygen. The oxygen has 2 lone pairs on it. A set up here and a set here. The same on this side. Double bonds to the oxygen. And some lone pairs. Okay, so there's the notes, and then keep out your tiles. You'll want them for the homework. The homework specifically, let's see. What was I doing today? 4.4 backside only and Lewis drawings only. So keep those out, put the notes away. Homework 4.4, backside only, okay. And the drawing, only doing the drawings. We don't have to worry about whatever E geometry is or M geometry. We're just doing homework 4.4. So this is homework 4.4 backside, and we're only going to draw the Lewis structures for today. This is where you're gonna just kind of trial and error your way through and thinking, okay, we know how to do some of them. Like we just did in the notes, we did ammonia and water. We did ammonia and water, so you still need to do them, but you can peek at the notes if you need. Draw those in there. And we also did CO2. So that'll be in your notes. That one is, those 3 you've already got drawn. Just redraw them. Some other ones, it gets a little tricky. HCN. The reason that the carbon is underlined is to help you see the structure. Like the carbon is in the middle, there's a hydrogen, then there's a carbon, then there's a nitrogen. There's several different kinds of carbon. Like, good Lord, there's like 4 different kinds of carbon. And we need a hydrogen. And there's also several different nitrogens going on. So first thing, just pick out all of the different kinds that you might possibly need. And I will do the same because I don't have them out. All right, so here are the 4 types of carbon. The double bond, like the 2 double bonds, single bonds, 3 and 1, and then this weird like twosie thing. And these are the 3 types of nitrogen: triple bond, single bonds, and then a double and a single. And we're trying to put them together to make HCN, hydrogen cyanide. The hydrogen, there's only 1 type, so we'll keep that. And that helps us a little bit because now we know, well, it can't be like this carbon because this carbon can only double bond on both sides. So how would it connect to that hydrogen? Well, it wouldn't. So we're going to get rid of it. That kind of helps in other ways too, because like this one could do a single bond here and maybe like double bond with the nitrogen, but you see how this is wrong because all of the black dots have to connect, like all of them have to connect. And this is like a single dot going into empty space. And this is a dot going into empty space. All the black dots need to connect. So this structure does not work. So let's get rid of this carbon option. We have 2 choices left for carbons. We can try this one. and this nitrogen. But again, we run into the same problem of like, we've got black dots extending into nothing. All of the black dots need to connect. So the only one that's going to work is if we do this carbon and the triple bonded nitrogen, like that. So on your paper, you would just draw H single bond to the carbon, which has a triple bond, 1, 2, 3, to the nitrogen, and the nitrogen has a lone pair. You can leave it like that, or draw a little dome around it. I'll do a couple more with you, and then I will leave the answer keys so that you can check your work. The next one, nitroxyl, has an H, N in the middle, O on the outside. So this nitrogen isn't going to work very well because the nitrogen needs to bond to an H and also an oxygen. So I'm thinking maybe this one's a good choice, because I can put that hydrogen here. And if I find the right oxygen, I can do a double bond there. So there would be my nitroxyl. Don't forget when you draw these that you got to have the lone pairs. So nitrogen single bonded to a hydrogen has a lone pair on it. Double bonded to an oxygen, and this is getting a little bit squishy, but the oxygen has 2 lone pairs on it as well. Okay, a few things. If you ever run into this issue on this next one, like CCl4, you look through all your tiles and you can't find a chlorine because I didn't give you a chlorine. What you're going to do instead is use elements that kind of are similar on the periodic table. So on the periodic table, chlorine is right underneath fluorine. Let me go grab a periodic table so I can show you. So chlorine is right here. Fluorine is right here. So things that are in the same column are going to behave similarly. If I ask you a question about a phosphorus, then use your nitrogens. So this is carbon with 4 chlorines around it. But if you want, you could just use F and do carbon with 4 fluorines around it, and then just switch the F to chlorine, in which case you would have, let's see, carbon and 4 of these around it. 1, 2, 3. I think I dropped one. Okay, if you ever lose a tile, like if you lose one, who cares? Just pick a different one that you need and make a little duplicate. Like this is my, technically this is my neon, but I'm going to like redraw it here because I can't find my other fluorine. So I'm just going to draw exactly a new tile. And now, haha, I've got my structure here. So this one, you could either convert the F's to chlorines or leave them, whatever you want. I'm going to do it the way it says chlorine. So I've got a carbon in the middle. I'd have some single bonds to chlorines. And each one would have 1, 2, 3, 4, 5. Each one is going to have boop, 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 some lone pairs on it. I probably won't put the little domes on this one, or I might get a little crowded. Okay, your sub or your teacher will have the answer key for this. And again, all you need to do, you don't need to worry about the E or the M or any of that. You just need to draw the Lewis structures that go here. We'll do more with this later, but we're not going to be able to do anything at all until you have your pictures drawn. So work on that, check your answers and make sure you've got 100 and that they're all correct before next time's class period.